the uncertainty, not uncertainty principle, the yeah, particle motions. Yes. So last time we did the problem of particle in a box. How to solve it? With the help of shooting the question and with the help of excuse me, with the help of what we have already learned from quantum mechanics, or from the principles of quantum mechanics, and we got some value of the energy, right? And that energy could be determined by another method as well, right? For example, if we want, we can use this as using the uncertainty principle to solve problems. In quantum mechanics, most of the time we do approximations, and and approximate solution is not a bad thing. It gives us some idea. So we can find the energy of kind of a particle that is confined to a certain space. For example, particle in a box. We can find its energy, kind of, right? Okay, so using the uncertainty principle, right, for the box energy. Right. We said that the box has dimensions of L by 2 or kind of L, right? And it's a one-dimensional box. So what will be the energy of a particle in it? We have a particle that is confined to it. And what will be the energy of the particle? So we can use the uncertainty principle, right, to approximate the energy of this particle. We know that the uncertainty principle says delta P, delta X is greater than or equal to H cut divided by 2, right? Now, we can replace P by energy. We know that energy is equal to P squared divided by 2m, right? So this means that delta E, right, could be delta E could be like delta P squared, right, and by 2m. Delta P squared, right, that is equal to 2m and 2 delta E. So if that is equation 2, we can put here the value of delta P, right, square here. So we can write delta E, right, greater than or equal to, right, h cut square divided by 2, h cut not square, oh yeah, h cut divided by 2, and that is what when we replace this, that will be equal to the square root, right? So the square root of, what did I do? delta P is equal to this, and delta P is equal to 2m delta E. Right? So I will write it here 2m and delta E, and that and delta x that is greater than or equal to h cut over 2, putting this here in this one. So I can take the square of this, right? So when I take the square, I'll say 2m into delta E and delta x squared, right? Greater than or equal to h cut over 2, or I can find the uncertainty in energy, right? Which is greater than or equal to h cut. Oh, well, that is square shaved, na? When we took the square, that is like kind of 4 or something. So h cut square divided by 4, and delta x square, right? Whatever. 2 and delta x square, right? And that is nearly equal to the minimum uncertainty, and the minimum energy could be like, or we can say the ground state energy, the smallest energy of a particle in an infinite potential well, or a one-dimensional box, right? So that will be x cut squared by 4, right? And what was delta x? That was L by 2, suppose, right? Yes, whole square. H cut square divided by will be like 2m L square, right? So that is very close to the actual.
4 na?
Huh?
4.
2. Okay. So like that. That is very nearly equal to what? Pi, right? And h cut square divided by 2m L square. That is the actual value. That's the actual value. Go on. Something. Okay? Okay. So look, the only difference is like pi is kind of 3 or something, right? So a very good approximation. So you can use the uncertainty principle to find even approximate solutions to problems if you want to know what the value nearly could be. Let us do another important aspect of quantum mechanics, and that is the continuity equation for probability. You know that here, is it clear here?
Yes.
This is the actual value, our approximate value is like this, very close to each other. And we got this from the uncertainty principle, right? Okay, so let us do continuity equation for probability. Do you remember the continuity equation?
No, not really.
Huh? Yeah. Continuity equation. It's not only in plasma, it's in basic physics. In your electromagnetic theory. And in your FSC, fluid dynamics.
Yes.
Continuity.
V1,
Right? And there is a continuity equation about charge. If you have done through the electromagnetism of Griffith, it's very beautifully solved and treated. The continuity equation. It's like the law of, in your fluid dynamics, it is equivalent to the law of conservation of mass. The decrease of density at one point is equal to the flow of mass at another point. the increase of mass at another point. X यहाँ पर disappear होगा तो that will appear at another place.
Yes, sir.
Right? And there is a law of conservation of charge, and the continuity equation is in increment, or it describes the law of conservation of charge. If the charge decreases, suppose, if the charge density decreases at one point, this is a very important equation in electromagnetic theory, the continuity equation, and it is equivalent to the law of conservation of charge. If the charge density increases at one point, it increases. There must be an inward flux of current, or if the charge density is decreasing in a volume. If the charge density is decreasing in a volume, there must be a divergence of current. Charge must be flowing out. अगर यहाँ पर चार्ज डिक्रीज हो रही है तो इसका मतलब है चार्ज यहाँ से बाहर जा रहा है, डिसअपियर नहीं हो रहा बल्कि यहाँ से बाहर जा रहा है. That is called the divergence. The negative rate of decrease of density, the negative rate of decrease of density of charge density, for example, H in a volume is equal to the divergence of current flux going outside through the boundaries. You know, are like the law of conservation of mass. If the density is decreasing at one point, there must be something flowing outside at the boundaries, through the boundaries. That is called the continuity equation, or the law of conservation of charge. And you know, the law of conservation of charge, it was like conservation of probability. Conservation of probability. Conservation of probability. Like, or we can say, the continuity equation for probability. The continuity equation for probability. For charge, we know, right? What we know for charge? For electromagnetism, right? The charge density decreasing in a volume. So that is like this, the integral of, this was for charge, the integral of rho drq. drq gives you the volume integral.
Yes, sir.
And the rate of change of this. The rate of change of, look, that's a charge per unit volume, and that is volume. So it is total charge. Yes. The rate of decrease of charge, right, at a point. If I put a negative sign over here, the rate of decrease of charge at a point with time. By rate I mean the derivative with respect to time. That is equal to the divergence of current. Divergence of current, right? Out of the volume. Positive divergence means something is coming out of the volume. There is a source. Positive divergence means there is a source of current. Like a chinala. The chini divergence for positive. There is something flowing out.
Yes.
There is a source. So, if there is a charge decreasing somewhere, it must be flowing out as current. And that is the law of conservation of charge. So, in this manner, we can prove that if probability is decreasing at one point, the probability must be increasing at another point. That is the law. That is the law of conservation of probability, right? So now we start with the Schrödinger equation. If we have to, the probability density. The probability density is like psi star, which is equal to psi modulus squared. If you remember, we defined the probability density. We have to put the probability density instead of the charge. Charge density की जगह हमने probability को लाना होगा, and the probability is आपको किस चीज से probability मिलती है? Psi. And psi star is equal to psi modulus square, and that is equal to the probability density. The probability
density.
And this is also called the Born approximation.
Yes, sir.
किसी को psi के मुताबिक कुछ पता नहीं था. When Schrödinger discovered his equation, he did not know what is meant by psi. Somebody asked him, Mr. Schrödinger, what is the meaning of psi? And he could not reply. I don't know. Some mathematical thing. But this was Born who gave a meaning to psi later on. He said, psi is nothing, we don't know psi. But we know psi star, or we know psi modulus square, which is equal to the probability density. So, for finding the probability density, we must go towards psi, and then take a psi star, and then multiply them. Yes. So psi, we get psi from Schrödinger equation. And there is rate of change, look, rate of change of the probability density. Therefore, we should use the time-dependent Schrödinger equation. Yes. Because there is a rate of change. Yes. So, we should use the time-dependent Schrödinger equation. Time-dependent
Schrödinger equation.
So this was like example, right? This is not our purpose. This is example in EMT, what you call the electromagnetic theory. This is an example in EMT, like an identical situation. So time-dependent Schrödinger equation, right? I h cut d by dt in one dimension, right? Psi is equal to h psi. This is the Schrödinger equation. I h cut d by dt of psi is equal to h psi, where the h is the Hamiltonian, which is the total energy.
Yes, sir.
Let that is equation number 1. Right? Okay. We want to bring it. Since this is related with space, dr, related with
Space.
therefore we have to bring space. So it means we have to convert this psi kit, which is nothing, to our real space. It means we have to take its projection on the x. So we have to multiply it with the bra x to make it psi of x, right? So look, multiply this with h dash d by dt, multiply this with x bra, h and multiply it with x bra. So what is this now? That is psi of x, right? Okay. So here, that is the clue for that. This is not the title. That is not what we are doing. So this will be I at cut d by dt of psi of x and t as well is equal to h and to psi of x into t. I will not write x and t, if I go forward, because we will.
It is understood.
Yeah, we understand that this is the situation. So in 3 dimension, I can write it, right? 3D. I as cos d by dt and psi r of rt at psi of rt.
In 3 dimensions.
Right? R h is equal to minus h cos square divided by 2m into del square. That is the kinetic energy. Plus V. V is a function of R. Right? And psi. Should I write? It's okay. And psi. We understand that psi is equal to psi r t. Okay. So that is equal to minus h cos square divided by 2m and to del square. Del square means d2 by dx squared. And psi, right? And plus v and psi. But that is equation number 1. Now, this is 2. Okay, yeah, this is equation number 2. Right? Now, we have to come toward psi modulus square, which should be like psi star. Therefore, we should make a star of it. So let us take the complex conjugate of this equation 2. Right? Star of equation by star of taking complex conjugate of equation 2. So that will be minus I h cos and d by dt and psi star, right, is equal to minus h cos square divided by 2m del square and psi star plus v and psi star. That is equation number 3, right? Now I want to come toward this thing. The the product rule of the derivative, right? If I want to come towards something like this, right? Psi. Then I have to write something like d psi star by dt and to psi plus psi star and to d psi by dt. This is my aim. This is my aim because this is equal to the density. This is my aim because this is equal to the probability density. So toward this aim, I need this and I need this. So how do I get it? Look, I should multiply equation 3. I should multiply equation 3 with what? Look, this is equation 3. I want to get this. What should I do? I should multiply equation 3 with psi. And I should multiply equation 2 with psi star. I should multiply equation 2 with psi to get this term. Then I should multiply, to get this term, I should multiply this equation with, this is the left side, this equation with psi star. And if I add them, there is a negative sign here. So it will not be like this. Therefore, I should subtract. Is it clear?
Yes.
Therefore, I should subtract. So, subtract equation 3 equation equation 3 times, I will say equation 3 times psi, equation 3 times
Psi.
from equation 2 times psi star.
Yes.
Clear?
Yes, sir.
Okay, then S will be equal to, and then I should subtract. So then will, yes.
Long equal one students.
Okay.
Mashe. Bar. The equation 2 times.
Doesn't लिख
Yes.
Just लिखिए गुरे. Okay, so that and psi star. So it will be I H cut, and then I want to take the I H cut common. So I'm taking the I H cut common, and this is the term. So I will write psi star and d psi by dt. And what was toward the right side? I'm not writing it. And the left side, right? Then this thing. So, and this will be plus because I'm subtracting this. Plus psi and d psi star by dt. Now on the right hand side. Now on the
Right hand.
right hand, I'm subtracting this from that other one. So that was minus h cut square divided by 2m del square psi, and there was a psi multiplication, right? I guess the psi star multiplication, psi star and del square psi and plus psi star and V. सही था ना? Or that was supposed to, now this one. So we have to subtract it. So this will become plus h cut square divided by 2m, and this is also multiplied to psi. So psi and del square psi star and minus and this also multiplied to psi and v and psi star. Okay, look, what can we do now? Here is a minus psi v psi star, but since here this is not like, this will not change, we will not change psi, similarly we will not change psi star. It's not a derivative, right? It's a v is a simple function of 1 over r. So this is not going to change these things. So we can say, right, that we bring here and psi star here. Because v is not going to change psi. V is not a derivative, right? So this will cancel with. This will cancel. So what we get here, look, what will be this equal to? I h cut d by dt and to psi star. Right?
Yes.
And that is equal to, I'm taking this minus h cut squared by 2m is common. So that will be psi star del square into psi minus, right? Psi and del square and psi star. Right? Okay. Now, let me divide it by h and by I. So d by dt and to, should I write it sine modulus squared? Sine modulus squared. That is equal to 1 h is gone with 1 h. So that will be minus h. 2im. Right? And this thing. Okay, you should, it's not very simple, but it actually comes out like taking it common from here. But it is not that simple, but fortunately, it behaves like that. So del and psi and minus psi and del and psi star. It seems like taking this common.
Yes, sir.
You know, we can say that take it out, but you know, it's not simple like that. But we can do it. It does not change this. Right? R. I can do it like this, minus d by dt, right? And P, I'm writing this as P, probability, which is a function of R and
Yes.
this is the probability density, not simple probability, the probability density. And that is equal to del dot h cut over 2I m, right? And psi star del into psi minus psi into del into psi star. That is a question number system. 5? 4. Look, the rate of decrease of probability at a point R is equal to the divergence of something. Divergence means swelling. You know, swelling like a balloon.
Yes.
That's divergence. So the rate of decrease of probability density is equal to the divergence of something, and this something we call the probability current. We call this is the probability current. that is the probability current density. The probability current density.
So psi star,
Yes. Right? Okay. So we can write minus d by dt p is equal to minus divergence of J. That is the continuity equation for probability. The continuity equation for probability. So the local probability is not conserved, right? But the universal probability is conserved. Probability decreasing somewhere, the probability density decreasing somewhere is equal to the divergence of the probability current density. So decreasing somewhere means increasing somewhere else. So yes, that is plus. There is no minus. There is plus.
there is plus, no minus. My mistakes are minus will go.
So this is the law of conservation of probability too. The law of conservation of probability density decreasing here, increasing there. So the universal probability remains right. Once you normalize in a problem, some example, some system that should remain normalized forever. An isolated system. Now, another important theorem in quantum mechanics, that is called Ehrenfest theorem. Okay? Ehrenfest theorem. The Ehrenfest theorem. Right? This theorem actually Ehrenfest, Ehrenfest. I hope I'm not misspelling his name. So this theorem actually relates quantum mechanics and classical mechanics. Ehrenfest theorem, what does it do?
Classical.
It relates classical mechanics to quantum mechanics. To prove that the two are the same, or to prove that quantum mechanics is applicable in classical regime as well, or to prove that classical mechanics is a special form of quantum mechanics, to show that classical mechanics is a special case of quantum mechanics. Classical mechanics is a special situation of quantum rules and principles. right? So this theorem says that the expectation values of quantum mechanical observables, they follow classical laws. The expectation values in quantum mechanics, they follow laws. We have some observable, we have its expectation value. So those expectation values must be following the classical laws, whatever laws they are, like Hamiltonian equation, Hamilton's equation and Lagrange's equation, or all those equations. And mathematically, right? d by dt of the expectation value of an observable omega, the rate of change of the expectation value of an observable omega, that is equal to minus I over h cut, right? And the expectation value of the commutator of that observable. The commutator of that observable with the Hamiltonian. No? The rate of change of the expectation value of an observable is equal to the expectation value of the commutator of that observable with the Hamiltonian. Only that you have to divide it by x plus. That is his theorem, right? So let us come to this theorem and see how does it work. We know that the expectation value is equal to, how do we get the expectation value? Sandwich. We sandwich it, right? And the equation of state. Sandwich it between two states. Since there is a d omega by dt, therefore we should also be taking a differential of this equation with time, right? So d by dt, that is equal to d by dt of this and that is like applying the chain rule, right? Or the product rule or something. So d by dt of psi, right? You can write the time derivative here. D by dt. No, it does not make any difference. Omega and to psi plus psi and to d omega by dt and to psi plus psi omega and to d psi by dt. Now, here is d omega by dt. Suppose we say that d omega is not a function of time. Omega is not equal to omega of time. Like omega, suppose omega is not explicitly a function of time.
Yes.
Then d omega by dt, that will be equal to 0, correct?
Yes.
And d by dt dt of omega, that will be equal to d psi by dt, right? And omega and psi plus this will become 0 plus psi and omega and d psi by dt. Now we can put the value of, look, we have to bring the Hamiltonian and we have to bring what? The psi by dt. We can get it from the time dependent Schrodinger equation. Hamiltonian and time dependence, they are both there in the time dependent Schrodinger equation.
Yes.
So I h cut partial psi by partial t equal to h psi. सही रखा ना? ये दामूंगा दो बार छोड़ d psi by dt is equal to minus I by h cut, right? And h psi. So that is equation number 3, and suppose that is 4. So 4 in 3. 4 in 3. So d by dt and to expectation value of omega equal to, so I h cut, sorry, I h with a minus sign, right? So minus I over h cut and capital H into psi, right? And here omega, right? Omega into psi plus psi omega, and here minus I by h cut into x psi. Right? Okay. So if I want to take this out from here,
Yes, sir.
this will become positive. When we take out anything from the bra, that will be taken as complex conjugate of it. So if I'm taking I out of here, so it will become what? Minus I will become plus I.
Yes, sir.
And that is constant.
Yes.
Right? And look, H is a Hamiltonian. I should also take the complex conjugate of that. But since it is a Hermitian operator,
Yes.
it's a real observable, real physical quantity, so I will not change.
Yes.
सही था ना?
Yes, sir.
No, da was it just a sign was the path she or da was the legal. Is it okay?
Yes.
I hope clear to everybody. Plus sine omega minus I by h cut and psi omega h and clear. Okay. If I take I over h common of everything, I can write this like psi h omega and psi minus psi omega h and psi, right? Now, d omega, d by dt of the expectation value of omega equal to I or h cut, and I can write these right what psi and each omega minus omega h into psi. Psi.
Yes.
And you can also write it like this, minus I by h cut into omega we get an interesting meaning from this equation as well. Look, we have any observable, whatever observable that is, right? If that commute with the Hamiltonian, then omega and h, the commutator will be equal to 0. If they commute, the commutator will be equal to 0. d omega by dt will be equal to 0. It means omega is equal to constant. So any observable which commute with the Hamiltonian, that will be a constant of motion.
Yes.
Any observable that commute with the Hamiltonian, that will be a constant of motion. That will not change with time. Let us do an example. Example. If omega equal to, you want to find the rate of change of position. If omega is equal to x, then by the Ehrenfest theorem, should be like this, right? D by dt of x of a expectation value of x, that will be equal to minus I by h cut and x and h. Right?
Yes.
Okay. Look, minus I by h cut and x and p square divided by 2m plus v of
X or R or
and clear minus I by H cut. I can write it like this: x p square divided by 2m. Huh? Let me write it like this. Right? And plus x and 2 v of x and expectation. Right? Functions of operators. We know from the functions of operators, you can write this as p dot p.
Yes.
P square is equal to
P
P dot P. So it should be like the commutator of A, B, C.
Yes.
Three operators. You can use like that.
Yeah.
There is a rule which shows how the functions of operators do. So in commutators, if this is a function of this,
Yes.
right? Or if here is a function, then you can take a derivative of this. That will be equal to something like p square divided by 2m, right? That is equal to x and p and d of p square and divided by dp. The p square divided by 2 multiply. And this is a comma. What is this?
Come.
So this will become what? Minus I by h cut x and p, and I'm taking the 2m common, okay, here 2mh 2mh. And the expectation value, okay, this and dp square divided by, sorry, the derivative of this. So that will be like 2p and expectation value plus, okay, x and v of x. This is x and v of x is, what is v of x? It's a function of x. And x and a function of x, they commute. X and a function of x,
They commute.
p and a function of p commute. P commute with p. X commute with p. Sorry, it does not commute with p. X commute with x. So this equal to 0. 0. So I will not write it here. Now 2 goes with 2, and that will be equal to minus I by 2m, m h cut and p, right? The x and p, what will be the value of x and p? Do you remember the commutator of x and p? H cut. and 2 is gone, so I will write P here. Right? I minus 1 multiplied by minus 1, that will become plus. So it will be like this, and H goes with H. So it will be like P, right, divided by M. نقطة سكونة نداوم سر V رازية. V is equal to P by M. Right? It will be like this. X dot is equal to P by the classical equation. P is equal to MV.
Yes.
So the expectation values of quantum mechanics obey classical laws. You know, X dot expectation value is equal to P by M. That's not equal to anyway, so the velocity is equal to P by M.
Yes.
The velocity is equal to RP is equal to MV, which is a classical equation. You know it.
Yes.
I will give you a homework. What if you want to take, right, its commutator, for omega is equal to P, what should be the situation? For omega is equal to P. Mungkin so go omega is equal. What equation will you get? Oliver, how will you get it? How will you get it? If you put x is equal to sorry, not x is equal to omega is equal to P here, then follow the steps and show what do you get logically. Right? So maybe tomorrow we might have some spin example from the spin. Right? I think that's yes.
So that explains the expectation of x p square is equal to
This one?
the IS.
This one? Okay. Look, you can do it by 2.